Hello guys, my name is Liu Ruijin, and I am a second-year PhD candidate in Xi'an Jiaotong University. Today, I'm going to introduce our research end-to-end lens shape prediction with transformers. The lens detection is the process of identifying lens markings as approximated curves, which is widely used for lane depth warning and adaptive cruise control in autonomous driving applications. The popular pipeline solves it in two steps: feature extraction plus post-processing. While useful, it's too inefficient. A typical method requires a segmentation module and additional post-processing to obtain final curves. Besides, it usually outputs a fixed number of lanes, which does not have good transfer and scaling performance. In a word, the whole pipeline is not end-to-end, so it is flawed in mobile applications. To tackle these issues, we reframe the architecture to directly output lens shape parameters. We design a lens shape model formulated by physical variables and camera parameters, which represent physical interpretation for parameters of network output. Besides, we develop a transformer-based network that summarizes non-local information, enabling it to capture lens, long-unseen structures, and context. Given an input image, our LSTR can output a flexible number of lengths and achieve great performance with the fewest parameters and computation costs. Here is our lens shape model. The details can be found in our paper. Here is LSTR architecture. Given an image I, a backbone extracts feature sequence I's, which is fed into a transformer to attend the whole representation space. Finally, several feed-forward networks are used to generate the curve parameters. To train the whole network after getting the curves, a Green fitting loss first performs a bipartial matching between predicted curves and ground truth lens sequences to find positives and negatives. Then, a fitting loss is applied to optimize lens-specific regression losses. In the results section, this table shows that the performance on two-sample benchmark without bells and whistles, our method achieves competitive accuracy and the lowest false positive rate with the fewest parameters and computation costs. As for application studies, we first investigate the effect of the lens shape model. This table shows that a high-order lens model and the shape consistency both benefit the accuracy. Then, we investigate the effect of the transformer encoder. Here we show the encoder attention maps. The orange-red point is occluded, so the encoder focuses on its red unobstructed context features. The pitch path point is not occluded, so the encoder shows clear, long-unseen structures. The light blue point is a lack of marking appearance, so encoder learns more global context, so that's the light green point. Similarly, we analyze the attention maps for the decoder. The decoder mainly focuses on open, slender structures, which can directly separate specific lens instances without additional processing. To better show the transferability of our method, we collect a much more complex dataset. Without any training procedure, the qualitative results show that our method even estimates accurate lens without ever seeing the net thing. In this work, we reframe the lens detection to directly output lens shape parameters, which are estimated by an end-to-end architecture. The whole method achieves state-of-the-art performance with the fewest parameters and computation costs. In the future, we expect improvements on backbones and transformers for a more optimal architecture. Finally, the PiTorch codes have been made public, and the pre-trained models have also been released. In this GitHub repo, the main features are listed here. And more importantly, it is training-friendly. Only 1.3 GPU memory is enough to reproduce the paper's result. Thanks for your attention. See you.